Hi everyone, welcome back to Algorithm Simplified. This week we are going to look at Leetcode number 10, which is regular expression matching. This is one of the most frequently seen interview questions, and it is a difficulty of hard, even though it may seem very easy at first. So let's start by reading the question prompt. Given an input string S and a pattern P, implement regular expression matching with support for the period and star characters, where the period character matches any single character, and the star character matches 0 or more of the preceding element. So in other words, we can say that this period character can refer to A, B, C, blah, 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 all the way, or Z. And the star character, if coupled with, let's say, some value like A, this means we can match with 0 to infinity A's. Okay, so basically, given support for these functions, the matching should cover the entire input string and not just a part of it. So you can look at these examples on your own time, and they're also available on the Leetcode website itself. But what I'm going to do is I'm going to draw your attention to these constraints right here. So these constraints say the following. Well, first, S and P are guaranteed to not be empty strings. And they're only going to contain valid characters accordingly. And for each star that appears in our pattern, we're always going to have some valid character to match in front of it. Okay, so let's not look at these examples. You can do so on your own time, but let's start by looking at an example that I came up with. So one of the first things that my mind jumped to was, wait a minute, can't I just go ahead and loop through the pattern or string, iterate through it either using a while or a for loop, and just check if at every single index the values match? Wouldn't that be super easy? So yes, my theory is correct, but only for certain cases. So for example, if we were at this case right here, and let's declare some, let's say some index I, representing where we are in S, and index J representing where we are in P, then if we do so for something simple like example 1, it totally works. We start at 0, 0, and we see that, hey, A is equal to A at these indices. That's great. We move forward. And then once we move forward here, we see that, well, since the period character can stand for anything, then it also is a match, and we move forward again, finishing the loop and returning true. So that's very efficient and works well for these simple examples. But what happens if we have a more complicated example like right here? So technically speaking, these two should match. Why? Well, C star can refer to 0 or more C's, right? Here we have 0 C's, and then we have 1 A. And then it followed by any single character any number of times. And we have B once, so this matches. But if we use the same iterative strategy, this becomes very difficult, right? So right away, we face a hurdle of at index 0, 0, we see that A and C don't match right away. It's very complicated, and this definitely is not a great way to do it, because unless you use some very fancy mechanic of checking, hey, is there a star afterwards? And even if there is a star afterwards, does this necessarily mean that we can just ignore and move onwards and see that there necessarily is another character that matches I in the future? Well, it's very complicated with a for loop. So this means we definitely cannot use it. So this is an example showing that just iterating through with a for or a while loop doesn't work. But this simple example does. So now that we know this, what do we have to do in order to solve it? Well, what about the following? What if instead of looking at it as iterating through a for loop, look at it as a way in which we can backtrack or a series of decision trees in which we can make a decision about how many of the PJs, so at some character here, how many PJs we can use when it is attached to a star, right? So at any decision node we are at with a star, we can either use one of the PJs to move on to the next stage, or we cannot use it and we can only use an empty string, right? Meaning that we don't use PJ and we simply move J forward by 2 to skip this term and move on to the next item over. So this sort of idea is a decision tree, and in particular, we're going to implement this using top-down dynamic programming with memoization. So more formally, this is what the algorithm looks like. So let's start off for simplicity by defining n and m as the length of our string and our pattern accordingly. And let's say that we are indeed at some I and j. Okay, so what we're trying to do right now is we're trying to find from starting at index I all the way until the end of S, and starting from index J all the way till the end of P, if those two strings match. So let's first look at what this means in terms of base cases. Well, there's going to be two bases we're going to encounter. First is if both I and J are finished, so they're past or equal to the length of n and m accordingly, it means we've traversed the entire two strings, both of them, and found out everything has matched so far. Therefore, we return true. But if J is greater than or equal to m and I is not greater than or equal to n, then we return false. And this makes sense because we've reached the end of our pattern, but we still have more strings to match. And in the problem, we are asked not to just match the partial string, but the entire input string. So if this case ever happens, we definitely return false. And now you might be thinking, hold on, wait a minute, but can't you say the same about I is greater than or equal to n? Well, not necessarily, right? Because let's say we had the following scenario. We had S is equal to, let's say, A. And then our pattern is equal to A star, B star, C star. Okay, so technically these two match, but if we returned false, if I is greater than or equal to m, what would happen in our algorithm is that there could be a possibility where we are at J right here with these terms still not traversed, but we're finished with A here because A and A star here match. Well, we still have more to go, but it doesn't necessarily mean that what we have left can't be an empty string and therefore match S. So returning at I is greater than or equal to n without checking the rest of the pattern is not logical. So that's why we don't have that third case right there. Okay, so those are our base cases. And given our base cases, what are our possibilities at every single decision, at every single ij node in our decision tree? Well, there are three possibilities. The first is if the term we're currently at, pj, is accompanied by a star. In this case, as we've described above, we can either use pj or just don't use it at all, right? So we can use one of the PJ, meaning that if we were at some A star, then we're just going to add a single A to our current string. Now, if this A is equal to what we're currently at in our string, then what we can do is we can indeed use this way, and we will just advance to I plus 1 and j. The reason being that since we've matched S, we can move on to the next I over. But since we've used one of A, doesn't mean we're done using A yet. Since we can use it infinitely many times, we still remain at the same J for the next decision node. But the other case doesn't really care if the two match, because they could match or they don't have to match. But the second case is saying like, hey, let's just treat this as 0. However many A's we've considered or whatever came before, we're going to treat this as an empty string. So then what we need to do is, well, we remain at the same I because nothing has been matched for I yet. But J needs to advance 2 places and not 1 because the next one over is our star. But the one after that is the next letter we need to look at, or the next character. For these two cases right here, where we do not have star as the next character over, if the characters match, meaning either PJ is the universal character period, or the two just physically match, then we advance forward 1 each to look at the next characters over. Okay, so this may be a bit difficult to understand without an illustration. So what I'm going to do now is I'm going to take this very difficult question that we couldn't solve with iteration before and apply it to our dynamic programming and draw it out. So what we're going to do is we're going to do top down, and we're going to start at 0, 0. So I is going to be 0, and j is also going to be 0, 0. Great. So since the next item over, index 1, is a star, then we can either use one C or we can use no C's at all. So let's say here we're going to use one C, and here we're just going to use nothing at all. So can we use this one C? Well, no, because at index 0, which is what we're currently on for I, that's A, and this is C. So since these two do not match, we return false. Okay, so then what we have to do is we have to look over here. So looking over here, what do we do? Well, since we're treating this and ignoring this, what we have to do is we have to move from index 0 to 1 to 2 to the next item over. So staying at the same I, moving 2 over to index 2. Now, looking at this, A, we don't have any star afterwards. So we have to check if at index 2 here, we match what's here at index 0. And indeed, A is equal to A, meaning we can move forward. So what we then have to do is we have to advance each index forward by 1 to look at the next item over. So now we're at B and this period right here. So since at index 3, the next over is indeed a star, what we have to do is we have 2 decisions. We can either use a period, or we use no period whatsoever. And if we use a period, what's going to happen is we're going to advance B forward. Why do we advance this forward? Well, the period matches any character, right? So using one of the period means we match B and we move B forward. So 2, and then we remain at the same 3. So here you can see this is a prime example of why we don't want to return false when when only I is greater than or equal to the length of S and not P, because it could be that everything else afterwards, so from here, is an empty string. So let's see what this looks like if we continue. So here at index 3, I can still have either the option, like before, to use a period or use nothing at all. If I use a period, well, that doesn't really work, right? Because if we advance S anymore, well, looking at S right here, we're already out of bounds. So out of bounds null character doesn't match with the period right here. So no, we return false since SI is out of bounds. But what if we just treat this as an empty string now? So we're done using the periods. Well, then what happens is that we will move forward to 2 and 4. And looking at 2 and 4, we've reached the base case because both I and j are greater than or equal to their respective lengths n and m. So we reached a base case, we return true because I is greater than or equal to n and j is greater than or equal to m. So you can definitely try to fill the other parts in on your own, but as you can see, this right here is the path to our solution. Returning true here, we use or statements at every single decision and return the or statement up. So here it's a true, here it's a false. The or statements give us a true, and then a true, and then a true all the way till the end, and that's what we return. And we cache each of these decisions in a cache. And this cache is going to be dimension m by n, right? Because that's how many possible entries there could be. And therefore, our our memory complexity is going to equal O of m times n. And what's our time complexity then? Well, our time complexity, at worst case, we're going to have to travel through every single one of the possible I and j's. And that's going to be m times n of them. So the time is going to be O of m times n. And that is going to be our time complexity and solution.
So I'm just about to show you my code solution for this problem, but before I do, if you've made it this far into the video and you appreciate this kind of content, I would really appreciate it if you could subscribe, like, and comment on this video because it helps me out in ways you couldn't believe. Because of your support and your subscriptions, this is why I'm able to do what I do and provide these explanations for Leetcode questions. So if you're enjoying the content, please do subscribe. Just takes a second. Okay, now let's get into the solution. So the solution implementation, I'm just going to write it out and speak out my logic as I go on along. So I'm going to declare some variables. So int n, int m. These are going to be the length of S and P accordingly. And then our array of array cache, which is going to be dimension m by m. And this is the is match function that we are supposed to solve, where we are given a string S and a string P. So first, let's make the global variables the correct values. So n is going to be s dot length, and m is also going to be p dot length. And then using n and m, I'm going to initialize the cache to be an n by m array. You can also use m by n, but this is just what I've been using. And here, I'm going to actually use n plus 1. And the reason being is that we are sometimes, like in the example, going to go 1 over the number of n, or the number of characters in S. So that's why we have to allow for one more n value in my implementation at least. And note that all of this is initialized to zeros, so all the values are initialized to zeros. And then what we're gonna do is we are going to call a helper function. I'm just gonna call it top down, and then I'm going to pass in some values. So let's fill that in later and write this helper function for now. So what this helper function will need is, it will return a Boolean, right? So it'll return a Boolean. It's going to be called top down, and what it's going to do is it's going to take in our current positions I and j, and then it's also going to have to take in the strings s and p. And now what we're first going to do in this recursive function is we're going to look at our base cases. So our first base case, remember, is if I is greater than or equal to n and j is greater than or equal to m, that means we've completed looking through all of the s string and also the pattern p string, and we can return true. Now, if it is the case that only j is greater than or equal to m and I is not greater than or equal to n, then we return false because we have no other pattern to follow our string that's left over. Okay. So now that we're done with looking at our base cases, we're first going to look at our cache to see if we've already calculated I and j. So we're going to look at cache and see if ij has already been calculated. So we're going to do if cache ij does not equal 0. So since they're all initialized to 0, I'm going to use that as a statement to check if they have been changed. So I'm going to use the cache at ij to store -1 if we return false there, and then 1 if it's true. So this is how I'm going to express that, and also I need to uncapitalize this. There we go. So if it's the case that the cache hasn't been changed at that ij position, it means we haven't calculated yet. So what we need to do now is we need to do the calculations. So my implementation is that I first declare a Boolean called characters match, which tells us if si and pj match. So if I is less than n and s dot character at I is equal to the p dot character at j, or our p dot character at j is equal to a period, then that is going to be our characters match. So let me make a comment there. This indicates if characters si and pj match. Okay. Now I'm going to initialize another Boolean called isMatch. So this isMatch indicates if the characters s from I until the end and p from j until the end match. All right, so I'm just going to initialize that. I'm going to call it isMatch. Okay. So how do we determine what isMatch is? Well, first, let's see, there's two cases, right? Remember, if there is a star or there is no star. So if j is less than m minus 1, meaning we're in the range to search for a star afterwards, and p dot character at j plus 1, so the next character over in our pattern is indeed a star, then isMatch is equal to, well, there's two possibilities, remember. So it can either have our top down I plus 1 and j with our s, same s and p, meaning that we use the current pj, but we can only do so if our characters match. And the reason why I put this in front is because if this fails, then I no longer need to waste the time to calculate this, right? So if I can either use pj if si is a match, or I can just not care and I can do top down I and then j plus 2, meaning we move over and disregard the character star that we're looking at, and then use the same s and p. So let me put in some brackets here to make it extra clear to the program. Okay, so to make this really clear, this is when we use 1 pj, and this is when we use 0 of the pj's, i.e. we just use an empty string. Okay, now the other case, this is when our star is not the next character. Then what we do is isMatch is only equal to if the characters match, right? So either the characters match, right, and top down of moving the two indices forward work. Great. So now what we're going to do, now that we've calculated isMatch, after we've done so recursively and we reach the base case and we come all the way back up to our ij, if the isMatch is true, so if everything matches, we're going to update our cache ij to be equal to 1. Otherwise, we're going to update it to be -1. And remember, the only reason why I implemented like this is just so that I understand when I have used the cache and when I haven't, right? Otherwise, I'm going to initialize to another number. I'm going to have to loop through n times m, and that's just going to take extra time. So this is just my implementation. You don't necessarily have to do this way, but hopefully that makes sense. And at the end, we're just going to return if it is a match at ij. So remember here for top down, our base case, or not our base case, where we start from is we start from the beginning, and then use the S and then the P. And let's see if this runs. Great.